Okay, that is what I'm left with. There's a 4 hours topic. You can just discuss those things, and you can expect simple problems. If you have studied the Faraday's first law, Faraday's second law, and then electromagnetic principles, electromagnetic induction principles, then that is sufficient for this chapter. Okay, so what we shall do, we shall just start. And then end of this session, so as scheduled, I'll be giving you the first event, that is MCQ, multiple choice questions. So there will be around 17 to 18 questions. So of 1 marks, and yeah. So at the end of this session, you'll be having that first event MCQs. Okay, so that will be of 20 marks for 15 minutes duration. So you'll have to complete it by 15 minutes, within 15 minutes, 20 questions. And the questions, you'll not be getting a calculation kind of thing. Somewhere, 2 or 3 questions, you'll be getting the calculation part. That will be straightforward. Okay. And the rest of the things are on the knowledge and the comprehension part. So if you know the fundamental concepts, you can easily answer it. So in order to avoid the copying or taking the data from the different sources, so I have reduced the time to 15 minutes, so 20 marks. Okay, so you have to submit it within the stipulated time. Else, I will stop the responses. I will stop the accepting responses after some time. So don't wait until you until the last minute. You just submit it well within the time. That means if the deadline is 3:20, you have to submit it by 3:18 itself. Don't wait up till the 3:20. Clear? And that's all. And no retest will be there. Try to complete it within the time. And second test, the second event means event number 2. We'll plan accordingly as per the schedule. Okay. So today we shall discuss about the mutual coupling or magnetically coupled circuits. So as you know, so the Faraday's first law and Faraday's second law. Okay, that means flux linking a coil which is changing with respect to time. So it might induce some voltage in that coil. That voltage is called the self-induced EMF. Okay, so that is nothing but your Faraday's first law. The second law is the rate of change of flux linking the coil decides the EMF. That means the EMF induced is directly proportional to the rate of change of the magnetic flux. Therefore, this develops the concept called as electromagnetic induction. Okay, Faraday's first law and Faraday's second law, or nothing but electromagnetic induction. All your DC machines, AC machines, transformers does work on the principle of electromagnetic induction. That is Faraday's first law and second law. Okay, so for example, if I write if I write a simple inductor like this, and if I try to pass a current over here, I of t, and this current is due to the supply voltage V of t, you will have some induced EMF in this coil due to this current. So due to this current, there will be some flux linking this coil. Due to the flux linkage, there will be some EMF induced. That is, I'll denote as what E of t. So this E of t will oppose the cause producing it according to your Lenz's law. So E of t will be exactly opposite to your the supply voltage, that is nothing but V of t. So this is your Faraday's first law and Lenz's law. Okay. So similarly, this is about a single coil. What is happening here? Current carrying conductor generating the EMF. That's all. Okay. Now, if I have some another coil which is in the vicinity of the other coil. Okay. So for example, here coil number 1 and this is coil number 2. So what does happen? I am connecting a supply voltage V of t. Therefore, a current flows I of t. Therefore, the flux will be generated phi of t, and that links the um, coil number 1. So the flux will be like this. So it will be linking this coil number 1. And as a result, this flux might also link this coil number 2 due to its vicinity with respect to the first coil. So now what is happening here, some part of this flux is linking this coil number 2. Therefore, what happens, an EMF will be induced here. So that is because of the induction effect between the coil number 1 and coil number 2. Okay, so what you can say here, the total flux is phi here. Some part of the flux is linking this coil number 2, that you can denote as what phi 1 2. So and the flux which is linking only the coil number 1 can be denoted as what phi 1 1. So therefore, your phi of t is equal to phi 1 1 plus phi 1 2. Phi 1 2 is a part of the flux which is produced in coil number 1 linking coil number 2. Due to this phi 1 2, you will have some voltage induced in this coil number 2. Okay, that voltage is called mutually induced EMF, or that EMF is called mutually induced EMF. Okay, so let us write the different voltages here. So due to flux phi 1 1, you will have some voltage E1 here, and due to this phi 1 2, you will have some voltage E1 2 here. So E1 here, as per the Lenz's law and the Faraday's law, so E1 is equal to minus N1 into d phi 1 by dt, d phi 1 by dt, and E12 is nothing but minus N2 into d phi 1 2 by dt. So this is what the mutually induced EMF in coil number 2 due to the change of flux in the coil number 1. Okay, so this is what the coupling and voltages due to this mutual induction. So you can also write E12 in terms of mutual inductance. So due to this flux linkage, so there may be some opposition for the linkage, or there may be some support for the linkage. That is called mutual inductance between the two coils. So that is denoted by M. Okay. So or else M12 you can denote it as. So therefore E12 can be written as minus M12 into dI1 by dt. So that is what you can write. So I1 is the current flowing in the first coil. Okay, that means the voltage is induced in the second coil due to the current flowing in the first coil. So that is nothing but mutually induced EMF. Okay, so therefore M12 can be denoted like this from this equation. So it's nothing but N2 into d∅12 by dt. So this is how you can understand the flux linkages and its effect. Okay, so similarly, what I can do, I can change the positions of the supply voltage. So what I will do, I'll just connect the uh, voltage source on the coil number 2, and let us observe what would happen now. So the voltage source is being connected here, therefore the current will flow here. As a result, some flux will be generated here. That generated flux will link the coil number 1. This is coil number 1 and this is coil number 2. So here it is phi22 you can call, and here you can call phi21, because phi21 is the flux produced in coil number 2 linking coil number 1, where phi22 is the flux produced in the coil number 2 due to the current flowing in coil number 2. Therefore, so phi2 is equal to what? Phi22 plus phi21. So this is how a flux linkage happens. And due to this, there exists some imaginary term that is called mutual inductance. So this mutual inductance, as before, you can write it as M21 or M12. So here I'll denote as M21. That is nothing but E21 generates E21 voltage, and that is nothing but minus M21 into di2 by dt, or E21 is equal to minus N2 into d∅21 by dt. So this is how you can understand the mutual inductance concept. So where your M1, that is M12 is equal to M21 is equal to M, that's a constant value. Whereas the coupling is bilateral, the coupling between the two coils is bilateral. That means it exhibits the same characteristics in both the directions. Okay, therefore M is equal to N2 into d∅12 by dt, that is equal to N1 into d∅21 by dt. You can either use any one of the expressions based on the knowledge of the flux linkages. Okay, so this is what the mutual inductance concept. So self-inductance you already know, and mutual inductance, I guess you have studied it before also. That is why, so I'm just going through quickly. Okay, so what about this coefficient of coupling? So what do you mean by the coefficient of coupling, and how it is understood in this concept of coupling circuits? Okay, so the coefficient of coupling is given by or denoted by coefficient of coupling, very important concept here. It is denoted by K. So when two coils have self-inductances L1 and L2, which are placed very close to each other, then the coefficient of coupling between these two can be denoted by K. That will be expressed in terms of the mutual inductance between them and the self-inductance, that is L1 and L2. So this is the expression for coefficient of coupling. I don't want to go through the derivation because you have already studied in your fundamentals of electrical engineering course. Okay, so K is going to be m into m divided by square root of L1 L2. So K value, the maximum value of K is 1 here. So when K is unity, the coupled coils are said to be tightly coupled or perfectly coupled. So when K is negligible, or when K is very less, you can say that they are loosely coupled. Okay. So this is how we can understand the coefficient of coupling. So for example here, so what would happen? So they are physically separated like this, and in the second case they are very much near to each other. So what would happen here, M here and here, M here, M1 or M2. So M here differs, and M1 here differs, and M2 here also differs. So because the amount of flux linking the coils would vary if they are placed away from each other, and the amount of flux increases, changing the flux increases when they are placed very close to each other. Therefore, the mutual inductance varies. As a result, the coefficient of coupling also varies. So when you say K is equal to 1, that means they are tightly coupled. They are very much close to each other, and all the flux generated in the first coil would be linking to the other coil. That means if K is equal to 0.9, that means 90% of the flux linking the second coil, which has been produced in the first coil. That is how you can understand. Okay, and if K happens to be is equal to 0.2, something like that, that means you can understand that only 20% of the flux generated in the first coil might link to the second coil due to its separation. Okay, so this is how the coefficient of coupling comes into picture here. Yeah, so this is the second concept here. And the third concept, very important, you might not have studied in your previous courses. So that is nothing but the dot convention. Dot convention, so very important. So in any competitive exams, you might expect a question on this one, dot convention. So once again, the power went. There's a power breakup. Okay, so dot convention, which is used to find the relative polarities, which is used to find the relative polarities of the voltages due to mutual inductance with respect to the voltages of self-inductance in the coupled coils. I repeat here, dot convention is used to find the relative polarities of the voltages due to mutual inductance with respect to the voltages of the self-inductance in the coupled coils. So for example here, there are two coils here. This is coil number 1 and coil number 2 here. So here E1 is the self-induced EMF in the coil 1, E2 is the self-induced EMF in the coil 2. Okay, so E12 is the self-induced in the coil 1 due to the flux or changing current in coil number 2. Similarly, E21 is the mutually induced EMF which is generated in the coil number 2 due to the current changing in coil number 1. This is how you can understand. Okay, E1, E2, and E12 and E21. Okay, so again a power breakup. So now these are what the self-induced EMF, and these are what the mutual EMF, mutually induced EMF. So I need to establish a relationship between these two, or I need to find the polarities of this mutual EMF with respect to the self-induced EMF, or self-inductance with respect to the mutual inductance. Like that, I have to find out the relationships. So as a result, there's a concept called as um, dot convention. Dot convention. So that is used here. Let me explain that one to you. So you have a coil like this, and just connected to supply voltage like this, and you have another coil like this, which is connected to the load like this. So what we do, we just write a dot like this here and dot like this here. So we mark the currents like this, I1, and I mark the current like this, I2. And due to this, I am having some mutual induced EMF due to this mutual inductance. Mutual inductance is not physically available for measurement. It has to be assumed that it is there. Okay, so now what is happening here? Due to this voltage V, there is a current I1. As a result, some flux is being generated in the coil number 1, and this flux links the coil number 2. Due to this change in flux, there is some voltage in the coil number 2, and due to that voltage, there is some current I2 which is flowing through ZL. I repeat here, there is some voltage. Due to this voltage, there is some current I1. Due to this current I1, there is some flux generated. This flux links the coil number 2 here. Due to this changing flux, an EMF is induced here. Due to this EMF, the current will be flowing through this inductance ZL. So I1 and I2. Okay. Now just follow me here. I1 is entering the dot here, and I2 is also entering the dotted terminal here. This is the dotted terminal, and this is the dotted terminal for the second coil. So I1 is also entering the dotted terminal. I2 is also entering the dotted terminal. That means the self-inductance and mutual inductance are having the same polarity. I repeat here, when the currents in both the coils are entering the dotted terminals or leaving the dotted terminals in a similar fashion, then you can say that the mutual inductance and the self-inductance are having the same polarities. I will apply KVL here, just follow me here. It is nothing but J times into XL1 into I1 plus J times into XM into I2 is equal to what? V1. This is the first equation. And next equation, J times into XM into I1 plus J times into XL2 into I2 plus one more quantity is there. It is I2 into ZL, that is equal to what? 0. This is equation number 2. So this is the voltage drop in the reactance due to current I1, and this is the voltage drop due to the reactance, that is mutual inductive reactance XM. Thus, that is created by the current I2, similar in similar fashion. So this is XM into I1, and this is X2 into I2. So just follow me here. All the polarities are same. So this is the self-induced EMF, and this is the mutually induced EMF, and this is a mutually induced EMF, and this is a self-induced EMF, all having the same polarities. Okay, I will change in the next case. Change the next case here. Follow me. So what I will do, I will just change the dotted positions here, and I will keep this as it is. So what would happen? And voltage is connected here. So I1 here, and this is connected here, and I2 here. So, and here between them M. So what is happening here? So I1 is leaving the dot here, whereas sorry, I1 is entering the dot here, I2 is leaving the dot. Any other way around, you can check out here. So in the second case, the polarity. In the second case, just check out here. I have written it differently. In both the case, um, in both the case, yes, I1 is leaving the dot, and again I2 is also leaving this dotted terminal. So here also, uh, the self-inductance and the mutual inductance will have same polarity, will have some same polarity. Okay, so I will change the scenario now. Okay, just check here. So now I1 and now I2. So now it is different. So I1 is entering here, but I2 is leaving this terminal. So let this be A terminal and this be B terminal here. So I1 is entering this A terminal, but I2 is leaving this B terminal. Okay. So like this, you can take out. And in such a case where um, the current, one current enters the dotted terminal and other current leaves the dotted terminal, the sign of the mutually induced EMF is opposite to the sign of the self-induced EMF. Okay, so in this case, you can write the KVL here with J times into XL1 into I1 minus J times into XLM into I2, that is equal to V1. Similarly, minus J times into XLM into I1 plus, okay, it is J times into XL2 plus Z2, that is equal to what? 0. Let's check out here. This is a self-induced EMF and this is a mutually induced EMF, and this is a self-induced EMF and this is a mutually induced. Sorry, this is a mutually induced EMF and the self-induced EMF. Therefore, you can observe that the polarities would be different. So usually what happens in all circuits which are magnetically coupled, um, there might be some markings like this dot convention. You need to check for that dot conventions. You can find these things on a transformer nameplate. Okay, on a transformer nameplate, because transformer is a static device which will be having two coils linked to one another. Okay, linked to one another, and then you can find those things with respect to the dotted terminals. Okay, so based on this, you can have two kinds of connections. Two kinds of connections. So coupled coils in series, and coupled coils in parallel. That means coils can be connected in series and coils can be connected in parallel. That means coils which carry same current are said to be in series. Coils which carry which is connected across same voltage, then it is said to be connected in parallel. So here also two things are possible. So the mutual inductance might aid the self-inductance or might oppose the self-inductance. Here also same thing. So the mutual inductance might aid the support the self-inductance or oppose the self-inductance. So like that, it might work here. Okay. So in exam, you can expect a question on this one, that is explain or compare coupled coils in series aiding or series in a series opposition, or coupled coils in parallel aiding and opposition. Okay. So let us discuss one by one. So coupled coils connected in series aiding now. So coupled coils connected in series aiding. That means the voltage gets add up. The voltage gets add up. All the voltage, that is self-induced EMFs, mutual induced EMFs, all gets add up. That is called series uh, aiding. So what I will do, I just write here, follow me. This is coil number 1 and this is coil number 2 here. They are carrying the same current. They are carrying the same current here. Okay. So the same current will flow here. That is I of t I can write here. I of t I can write here. So what happens here? There will be some first for the voltage. The voltage due to self-inductance, I will denote this as E1, which opposes the cause producing it. Okay. So this is one, and due to this also current, this is L1 and this is L2, there will be some current in this coil also. Therefore there will be some voltage induced. That voltage is nothing but E2, self-induced in coil number 2. Now what happens? There is some flux generated in the coil, and this flux links these coils like this. Okay. So what might happen here? The flux produced in coil number 1 links coil number 2, and the flux produced in coil number 2 links coil number 1. So therefore, there are two voltages produced in coil number 1 and coil number 2. So the first voltage I will write here, that is nothing but E21. That is nothing but the voltage produced in coil number 1 due to the flux in the coil number 2. Similarly, I can write like this. So E12, where this is the voltage due in coil number 2 due to the flux in changing in the coil number 1. So there are 4 voltages now. So all voltages are in the same directions. Therefore, you can add them, E1 plus E2 plus E12 plus E21. So that is equal to what? Total voltage in the circuit, which is connected in series. I guess you have understood. Okay. And between them, there is what? A mutual inductance M. Between the coils, you have got the mutual inductance M. So what are the equations for the different voltages? So let us write that one. So E1 is what? The self-induced EMF. That is nothing but minus L1 into di by dt. Only one current is flowing. E2 minus L2 by L2 into di by dt. E21, it is nothing but minus m into di by dt. E12, it is also minus m into di by dt because current is remaining same through the two coils. Is it clear? So this is how you can uh, explain series this thing. So you can say, sir, what about the dot convention? So to dot convention can be like this. You can put a dot over here and you can put a dot over here. So the to have the same polarities for mutual inductance and self-inductances, the currents should either enter or leave the dotted terminals. So in this case, these are the dots here. I mentioned the dots here. So what is happening here? The current is entering this dot, and the current also here is entering the dot. Therefore, the polarities are same in all the four cases. Okay. So this is called series aiding. Now let us change the dot convention for to some extent. So what might happen? Let me check here. So I will change the direction here. So this is L1, this is L2 now. So current now it is flowing here, which is entering here, not here. So therefore, in coil number 1, the current is entering the dot, and coil number 2, the current is leaving the dot. The current is leaving the dot here. So therefore, so what would happen? So E is equal to E1 plus E2 minus E21 and minus E12. So you can mark here. So here it is E1 and the other way around is E21, and here it is E2. The other way around is sorry, this is E12 and here it is E2, like this. Okay, so it is minus minus and this is plus and plus here. They are in opposition. They are in opposition. Okay. Yes. So this is about the coils connected in series opposition. Okay. So now, so we should take up the coupled coils in parallel aiding. Coupled coils in parallel aiding. This is a series opposition, and this is parallel aiding. So let's write it here. Coils has to be connected in parallel. That's all. Coils has to be connected in parallel. So dot I will write here and I will write here. So what happens here? I is coming here. So I1 here and I2 here. So this is L1 and this is L2. So what is happening here? Both the currents are entering the dotted terminals. Both the currents are entering the dotted terminals. Okay. So other way around, you can change the circuit. So what would happen? I'll change the dotted portion here. Current is leaving the dotted terminal on L2, and current is entering the dotted terminal on L1. Okay, so this is how we can distinguish. This is parallel opposition, parallel opposition coils, and here also you can have mutual inductance, and here also you can have the mutual inductance. So the voltage is remaining same here. Therefore, V is equal to the first case J into XL1 into I1 plus J into XM into I2. Similarly, V is equal to J into XM into I1 plus J into XL2 into I2. This is the first case equations. The second case equations, check out here, follow me. V is equal to, okay, J into XL1 into I1 minus J into XM into I2, and V is equal to minus JXM into I1 plus J into XL2 into I2. That's all. Clear? So this is how you can deduce the expressions. Now, what is that you can also expect? So you can find the equivalent impedance in both the cases. So just add it here. So in the first case, you are adding all the voltages. Therefore, the total equivalent impedance here, it is nothing but L1 plus L2 plus 2M. There is a total inductance in the first case. In the second case, so what happens here? So L is equal to L1 plus L2 minus 2M here. Minus 2M here. So here in parallel aiding, we have to find out equivalent impedance because the inductance are connected in parallel. So I'll write the equation here directly. L1 L2 minus M square by L1 plus L2 minus 2M. So this you might have studied in your basic electrical. Okay. So similarly here, so what happens here? It is L is equal to L1 L2 minus M square divided by L1 L2 plus 2M. This is what the effective inductance when connected in parallel, and effective inductance when connected in series. Okay, so these are the concepts in the topic, the coupled circuits, and in the next session, so we shall solve some problems here, and then we shall conclude the chapter, conclude this coupled circuits. Okay, so if you have got any doubts, you can ask me.